In section 7, we're going to work with identifying and graphing linear and squaring functions, identifying and graphing cubic, square root, and reciprocal functions, identifying and graphing step and other types of piecewise functions, and recognizing the graphs of parent functions. So you notice like identify and graph, identify and graph. Mostly this is about being able to visually recognize, identify and recognize different types of functions. So when we're talking about writing out a linear function, right? This is the graph of a line. Linear functions are going to end up in this form, y is equal to mx plus b. They've given me f of negative 2 is equal to 6. That's the same as giving me a point, negative 2, 6. Right? This would be an x, and that would be a y. This would be an x, and that would be a y. So they've given me 2 points. So you can take them out of this reference, this type of a notation. You could put them into ordered pairs. I could put them into a t-table. Either way, I've got 2 points, and that allows me to use point slope in order to find this. So let's say that y minus 6 is equal to the slope, which would be found by the change in y. Let's say 6 minus negative 9. Over the change in x, so negative 2 minus 4, times x minus negative 2, which would be x plus 2. So all I've done here is I've taken, sometimes in examples I've done with you before, I've calculated slope separately and plug it in here, but I could put it all into one item here without any trouble. Y minus 6, excuse me, my mistake. Y minus 6 would be equal to 6 minus negative 9, that's 6 plus 9 is 15, over negative 2 minus 4, that's negative 6, times x plus 2. And if I simplify this by factoring a 3 out of each item, this would be negative 5 halves times x minus 2. X plus 2. When I distribute that, I'll get y minus 6 is equal to negative 5 halves x minus 5. So when I do negative 5 halves times 2, the 2's cancel and I just get minus 5. And now if I add 6 to either side, y is equal to negative 5 halves x plus 1. And now I've written my equation. Okay, so we identified 2 points. Use the 2 points to create slope, and then use the point slope formula. Okay, this is also referred to by the trigonometry textbook as the 2-point formula instead of point slope. We also want to talk about recognizing special types of functions. These are the constant function and the identity function. So a constant function, you'll notice, is just a straight line. The output is constant. That would look something like y is equal to, in this case, say 1 1/3, something like that. That's what they look like as equations, and this is what they look like as graphs. It's got a slope of 0 because all the outputs are the same. They're all a constant. And in this case, this is the same as saying y is equal to x. The inputs and the outputs all match. You've got a line with a slope of 1. This is called the identity function. For every value of x I plug in, the same value is going to be the y is going to be the output. So whatever you plug in as an input becomes the output. That's identity. This is a graph of a squaring function, right, where we call them a quadratic function. It always is going to be a parabola. It's going to open up or it's going to open down. This is the parent form, y is equal to x squared. And you notice you're going to have a vertex and an item that is symmetrical arranged around the vertex. So the left half is identical to the right half. If we look at a cubic function, this is a cubic function. It has some, you notice that either end does opposite things. With the squared function, the ends did the same thing. So in the squared function, the left end goes up, the right end goes up. In the cubic function, the right end goes up, the left end goes down. The domain of a cubic function is a set of all real numbers. The range is a set of all real numbers. This is an odd function because it's symmetrical to the origin, right? It's symmetrical around the origin. It has an intercept of 0, 0. It's an odd function, and the graph is increasing on the interval from negative infinity to positive infinity. These are all the characteristics of a cubic function. A square root function is a little different. This is what a square root function looks like. Y is equal to the square root of x. The domain of the function is a set of all non-negative real numbers. Non-negative, that's important, right? 0 works, but -1 does not. The range of the function is the set of all non-negative real numbers, meaning it can't have a negative output. It has an intercept of 0, 0, and the graph is increasing on the interval from 0 to positive infinity. These are all, by the way, what we would call parent functions. They're all very, they're in the simplest form for the type of function that they are. This is a reciprocal function. The graph is a hyperbola. Right? The domain is a function of negative infinity 0 union 0 to infinity. So you've got this split in the middle from negative infinity to 0 and then from 0 to positive infinity. And there are asymptotes, vertical and horizontal asymptotes, that cause the range to do the same thing. Right? So the horizontal asymptote splits the range in half. The vertical asymptote splits the domain in half. So again, it can go up to, but it's not going to include 0. The function is an odd function. It's symmetrical around the origin. It does not have any intercepts. It never hits the axes at all. And it's decreasing, right, from in each of the different intervals. It's symmetrical with respect to the origin. Okay, when we talk about a piecewise function, this is a piecewise function that is called a step function. And this one's kind of unique because it's for each interval that's identified in the piecewise function, the x value and the y value are the same. So this is like the identity form of a piecewise function. In fact, if you took the line from an identity function, you'll notice that if I connect the solid dots that form the ends of these intervals, it makes the identity function for a linear function. All right? And what happens is, it's like if I took this and I chopped it up into pieces of line that were a length of 1 and just laid them down to be horizontal. Okay, so that's sort of what this looks like. It's a unique form of, very specific and unique form of piecewise function. Piecewise functions, again, have different rules for each different range. If I want to evaluate a piecewise function, it depends on what value I use. Now remember, another way I could write this is that y is equal to x plus 2, but I use it only for intervals of integers. Right? So with this guy, and we can go back actually to take a look at the other function. Negative 1 1/2, that's over here. You'll notice that goes to the nearest whole number, which would be -2. Okay, so you don't use fractions in this type of a function. So you're using, that's what these little brackets are saying. They're using just integers. So when this one would go to -2, right? The function of -3/2 would be the nearest integer, right? -2 plus 2, which would be 0. And for the next one, f of 1 would be 1 plus 2, which would be 3. And the function of -5/2, right? 2 1/2 would be -3 plus 2, which would be -1. Okay, so it's a little funky in terms of the way these piecewise functions work. And this double bracket is talking about we're going to take all of these guys and sort of round them into whole integers. Okay, here's another type of piecewise function if I want to do a graph. And with the piecewise function in this case, it's not a step function. It's splitting the x-axis into two parts. And that's what these rules say. So if you go to where x is -4, you'll see these both relate to -4, 1, 2, 3, 4. What basically is going to happen here, 1, 2, 3, 4, what's basically going to happen here is at this blue line, we're going to shift from one function to the other. So for all the values of x that are less than or equal to -4, I'm going to use one function. So that would be starting here and all the values of x going in that direction, but including this point, I'm going to use this graph, -1/2 x minus 6. So let's go ahead and graph that. I'm going to do a t-table. It's a line. That's a linear function. And I'm going to use -4 because I want to find out what it does right there on that line. And then something on this side. So we could just do something else like -6 or something like that. Right? Anything over here would do. Sorry. As the other x value. I haven't found the y value yet. So when I plug -4 in, I'll have -1/2 times -4 minus 6. So -1/2 times -4 is 2, minus 6 is -4. So 1, 2, 3, 4. And I'm making a closed dot because this says or equal to, so it includes this point. When I plug in -6, -6 times -1/2 is 3. Minus 6, so 3 minus 6 is -3. So it goes up a little bit. Oh, I'm sorry. It would be, I used -6, so it's over there. Not at -5. And then when I graph this, it's going to look like that. Now if I look at the other half of the graph, for my values where x was greater than -4, which means it doesn't include 4, so it gets this open dot. I'm going to do an input-output table for that one as well. Right? This was -1/2 x minus 6. So I'm going to do a t-table as well for that. And I'm going to use -4 and something else. Let's say I use 0, right? Because it's an easy number. It's off to the right here. And this is for the x plus 5 equation. So -4 plus 5 is 1. And 0 plus 5 is 5. So over here I'd have an open dot at -4, 1. And then 1, 2, 3, 4, 5. Here's my next point. And I would go ahead and graph like that. So that's what a piecewise function looks like. The x-axis is split into different parts, and I use one graph for each part of the x-axis that has been split up. So over here, it was -1/2 x minus 6. Over here, it was x plus 5. Okay? The last thing we want to do is make sure we recognize the graphs of all these parent functions, the most common items that you're going to encounter. So we have the constant function, which is a horizontal line. The identity function we talked about, which is a line with a slope of 1 that passes through the origin. An absolute value function has a vertex at the origin and a slope of 1 going up to the right and a slope of -1 going up to the left. This is what a square root function looks like. A quadratic function, which they also refer to as a squared function. This is a cubic function. Again, you notice that on even powers, the ends do the same thing. On odd powers, the ends do opposite things. This is what a reciprocal function looks like. They also might be called a rational function. This is what a greatest integer function looks like. right? That's what this is called, the greatest integer function. And those are the basic parent functions. Now, when you have a parent function, when you add more parts into the equation, it will move the graph to different locations on the Cartesian plane, and it also may change its shape a little bit. Okay, so the quadratic function may have its vertex move to a different location. It may become wider or narrower. The cubic function may also move to a different part of the Cartesian plane, and its curves may become more humped or less humped. Just depends. Okay, in the summary, we wanted to make sure that we looked at how to identify and graph linear functions and squaring functions, meaning linear equations and quadratic functions. We want to identify different functions. We wanted to graph step and other types of piecewise functions, and we wanted to understand what the graphs of different parent functions look like.